Hey Coach L and Mr. Miller, this is the tutorial for reading the onboard accelerometer. Let's go. This is the basic code for controlling a motor using an accelerometer. We're going to use the onboard accelerometer of the 101 board as an input to control a motor based on the orientation in space. So if we tell the Arduino to the left, the motor spins one direction. If we tilt it to the right, it'll spin in the opposite direction. And if it is flat, the motor will stop. So the first thing we're going to do is we're going to include the Curie IMU library using the include function here. Then we're going to create three constant integers for the accelerometer. So the DRIA is connected to digital input pin 4, DRIB is connected to pin 5, and the PWM is connected to pin 6. For comparison, the previous orientation will start at -1. Then we get to the void setup. We're going to set the motor control pins as outputs. So using the pin mode function, we're going to set the DIRA and the DIRB and the PWM as outputs. And we're going to use the Curie IMU dot begin to start the accelerometer. We're going to set the accelerometer range to 2G using the Curie IMU dot set accelerometer range to 2. And then we're going to get to the void loop. So that's all set up. When we get to void loop, we're going to use the integers x, y, and z, and we're going to have the integer x equal the x-axis of the accelerometer using the Curie IMU reading the accelerometer function. We're going to have integer y equal the y-axis, and the integer z equal the z-axis. We're then going to use absolute value x, the absolute value function here to calculate the absolute values and determine the largest absolute value between x, y, and z. Using integer absolute value x equals the absolute value of x, and so same for y and z. We're then going to use if statements here to control when the motor is going to spin. So if absolute value of z is greater than the absolute value of x and the absolute value of z is greater than the absolute value of y, this is what's going to happen. So if z is greater than 0, we're just going to have everything break, so the motor's not going to move. And so then that's just the base function. And so we're going to use this else if statement here. So if y is greater than x and z, it's on edge, so it means it's being moved. So if absolute value of y is greater than x and it's greater than z, the following code is going to happen. So if y is positive orientation, y is greater than 0, we're going to set it the accelerometer to 1 and make the motor go forward. If it's the negative orientation, so the opposite way the board is being turned, the accelerometer is going to be turned set to 2, and the motor is going to turn reverse. Then we're going to get down here to the void forward here, and this is a custom function for driving the motor forward. We're just going to use this digital right function here to set the DRIA to high, the DRB to low, and the PWM to high, so by turning it in the forward direction. We're then going to also have a void reverse function here to control the motor when it's driving in reverse. It's going to be the same as before, except now the DRIRA is set to low, and the DRIB is set to high, and the PWM is also set to high. Again, we're going to then make a void break function here for breaking the motor, and the digital right 3 static lines of code here is going to be the same, except we're setting all of them to low, so no movement will occur. And there we go. This is the basic code for reading the onboard accelerometer. So here we have the accelerometer here, and we're going to have it attached to the 5.5 volts through this yellow wire here, onto the connection to the positive column here, and it's going to connect to the yellow wire here. Then we're going to have the board connecting to the 3.3 volts as well through this red wire here, and then this red wire here into the board at 3.3 volts. We're then going to ground the board by connecting it through this gray wire to the negative column, which is grounded by this black wire. And then we're going to be connecting the motor itself into these two pins here. So the ground wire of the motor is connected to this pin here, and then the red wire is connected to the pin here. and then it is all grounded again by this gray wire here. On the other side, we have the board connecting to the 3.3 volts through this red wire here. Again, 3.3 volts is over here. And then we have our pins controlling the motor and the different directions of the motor. So this first wire here is connected to pin number, here we go, pin number 4 on the Arduino board. That's the pin number DIRA on the board here. This next orange wire here, this next orange wire here is connected to pin number 5 on the board. It's connecting our digital input pin on the board here to DRI B on the pin on this board here. And then this yellow wire here is the PWM pin of the board connecting to pin number 6 on the Arduino. And then it is grounded by this gray wire here by connecting to this negative column. And then this black wire here grounds all the wires connected to this negative column by going through it into the negative column here, and that's grounded by this black wire as well. So now we can see it work by just, if we move it here, and move this. One way, and then if we go the other way, there you go. This is the modified code for reading the onboard accelerometer. So what we're going to do is we're going to, again, use the onboard accelerometer to control, as an input to control the motor based on the orientation in space. We've, including the y-axis, we've also added the x-axis variable. So we can now turn in all 4 directions, and it will affect the motor. Also in this code, we're having a different LED will turn on for each direction the board is turned in the x and y axis. And a piezo buzzer will also play depending on the direction of the motor. So if it's running forward, the piezo buzzer will play with increasing frequency, and if the motor is running in reverse, then the piezo buzzer will play with decreasing frequency. So let's go into it. Again, we're including the Curie IMU library. We're having the 3 constant integers of the accelerometer. Here we're going to create an integer I using the integer function here, and we're going to create constant integers for our buzzer pin for digital input pin 3. And then constant integers for our 4 LEDs on 10, 9, 8, and 7. We get to void setup. Again, we're using the pin mode function to set our accelerometer pins as outputs, and we're using the Curie IMU to start the dot begin to start the accelerometer. We're also going to set the accelerometer range of 2G using the Curie IMU set accelerometer range again, and then we're also going to use serial dot begin 9600 to start our serial monitor. As we get down here, we're using the integer x, y, and z to read the accelerometer again for the x, y, and z axes. And then we're going to calculate the absolute values to determine the largest using the integer absolute value x, y, and z using the absolute value function here. So if for the first statement, if absolute value z is greater than absolute value x and absolute value z is greater than absolute value y, we're going to have this is what's going to happen. So if z is greater than 0, we're going to have the motor break. We're also going to have no tone play, and all the LEDs will be turned off using this digital write function here. We're also going to use the serial print ln to print on our serial monitor that the motor is off, the LED is off, and no tone is playing. We're going to use the else if function here to say if y is greater than x and z, it is on the edge. And so if y is a positive orientation, then we're going to have the serial monitor print out the y value first. So y equals the y value, and then we're going to print a space here. The motor is going to turn forward, and then we're going to turn LED 1 on high using the digital write function. So that LED 1 is going to turn on. Again, using the digital write functions, all the other LEDs will be set to low or off. We're going to use the serial print function here to print what's going on, the motor forward, LED 1 on, and tone increasing. For the tone increasing, we are using this fourth statement here. So we're going to set I as 32, the lowest tone for the piezo buzzer, and as long as I is less than or equal to 1,000, I will be increasing. So then we're going to get, in order for this to work, we're going to have the tone function here, so it will be sent to pin 3, which is where the piezo is attached to, and at frequency in hertz as of I. We're going to delay for 10 milliseconds, and then we're going to set it to no tone to that pin or buzzer pin. We're then going to, once that keeps going, we're going to then set all the LEDs to low or off using the digital write function again, and we're just going to print that all the LEDs are off on our serial monitor using the serial print ln function. So then if the Y is in the negative orientation, we're going to do the same thing but opposite. So we're printing out the Y value on our serial monitor. The motor will be turning in reverse here, and we're going to use the digital write function here to turn on LED 2 this time, and turning all the other LEDs off. Again, we're printing what's going on, motor reverse, LED 2 on, and tone is decreasing. In order for it to help to make the tone decrease, we're going to set I equal to 1,000, and as long as I is greater than or equal to 0, I will be subtracted by 1 each time. Again, using the tone function here, sending it to pin number 3, and frequency of I. Delaying again, and then using the no tone function to shut it off. We're then again setting all the LEDs off using the digital write function, and then we're going to use the serial print function again to print that the LEDs are off. Now here we've added the X plane, so if it'll be turning instead of left and right, up and down. So if X is greater than Y on its edge, using the else function here, absolute value X is greater than absolute value Y, and absolute value X is greater than absolute value of Z. So we can have this is what is going to happen. So if X is positive orientation, then we're going to print out the X value on the serial monitor. The motor will be turning in the forward direction, and LED 3 will be turned on high using the digital write function, and then all the other LEDs will be turned on low or off using the digital write function. Again, using serial print to print out what is going on, and using this for statement, that the same one as above for the forward of the Y axis. I is equal to 32. If it's less than or equal to 1,000, I will be increasing. Tone, send it to pin 3, frequency I, delay for 10 milliseconds, and then turn off using the no tone function. Again, turning all LEDs off at the end, and then printing the LEDs off in our serial monitor. Lastly, for the final direction, the X will be in the negative orientation, so we're just using this else function here. We're printing the X value in the serial monitor using the serial print function. The motor shall be going in reverse, and then we're going to use the digital write function again to turn off all LEDs 1, 2, and 3 on low, and then setting LED 4 to high or on. Printing using the serial print function again to print what is happening, motor reverse, LED 4 on, tone is decreasing. To have the tone decreasing, we're going to use that same for statement as we did above for the Y reverse motor. So we're going to have I is equal to 1,000. When it's greater or equal to 32, we're going to have I decrease. So tone again is equal to the tone. Using the tone function, we're going to send it to pin 3 at frequency I, delay for 10 milliseconds, and use the no tone function to turn it off. Again, ending that with turning all the LEDs off at the end and printing that out on the serial monitor. Here, this is the same code as before. The custom functions for driving the motor forward. For void forward, you're just setting the DRI using the digital write function to high or on, and the PWM on high. The custom function for reverse, setting the digital DRB on high and PWM on high and DRI on low. And then for the brake, we're setting all of the pins to low. So there's that. And then if we get to the serial monitor, here's the serial monitor working. We can see, this is the modified board for reading the onboard accelerometer. So here we have the accelerometer still hooked up the same way as before, with the same wires and the same pins. But now we've added a potentiometer here. The positive side is connected through this yellow wire here to pin number 3 on the Arduino board. You can see that. And then it is grounded through its negative side through this gray wire into the negative column of the Arduino board, and then grounded again by this black wire. We then also have 4 LEDs set up, LED 1, 2, 3, and 4. All of them are grounded by their cathodes connecting into this negative column here and grounded by this black wire. They all also have a 100 ohm resistor here that they will connect to their pins. So this first LED here is connected by this white wire here to pin number 10. LED 2 is connected through this yellow wire here to pin number 9. This LED 3 here is connected through this green wire here to pin number 8. Then finally we have the last LED here that is connected through this blue wire to pin number 7 on the board. Okay, so now we can see it working. So if we go for the y-axis, y-axis again the other way, and you can hear the piezo buzzer. X-axis. So you can see as